Hello, fellow scholars. It's my great honor to be invited to this conference. My name is PENGCENG, and I'm from Beijing University of Technology. My research topic is a Fundus image myopia diagnosis model based on homogeneous multimodal feature fusion. The content of this presentation is as follows. First, we will discuss about the introduction. Secondly, the method. Then the experiments and the results. And finally, I will share my conclusion. According to the Urbanization and Human Development Index in the World Vision Report, issued by the World Health Organization, the myopia population will increase from 1.95 billion in 2010 to 3.36 billion in 2030, including 3.12 billion people under the age of 19, and the number is still rising. So it's very necessary for us to pay attention to children's vision problems. For the analysis of eye disease, fundus images are important for ophthalmologists, but medical resource imbalance of regions with different levels of development is a problem. So we need big data-driven deep learning and medical imaging as auxiliary diagnostic tools. Actually, in recent years, many achievements in combining big data-driven deep learning with medical imaging as auxiliary diagnostic tools have emerged. Among them, there are already some studies on the application of fundus images. Based on them, we found that vascular is one momentous factor in the diagnosis of ocular disease. So we try to combine the vascular and the original image to build a homogeneous multimodal neural network. The overall framework is shown in Figure 1. It includes an image processor and a classifier. The result of the processor will output the vascular feature image and send it to the classifier together with the original image. And finally, output the classification results, that is high myopia and non-high myopia. As shown in Figure 2, I'll introduce the image processor first, which consists of 5 steps. They are ORI selection, adaptive media filtering, blackhead transform, threshold filtering, and fusing clustering methods. Through them, the fundus image will transfer to binary image of vascular. The first step is ORI selection. In the process of observing the image, we found that the 4 corner areas in the image are all unique features, and their pixel values interfere with the final classifier. As shown in the blue data in the figure, there are a large number of unique pixels in the range of 0 to 10. Refer to the formula on the left to generate a mask matrix and perform a logical AND operation on the original image, and finally obtain the ORI image. The second is the adaptive media filtering. The feature of vascular is the fusiness of the boundary, so we abandon the linear filter and use the nonlinear media filter instead to protect the information. As shown in Figure 4, it can be found that the algorithm can enhance the vascular features while protecting the vascular boundary and has a particular noise reduction effect. Then the blackhead transformation. As shown in the formula, the first item represents the morphological closing operation. The second item represents the original image. The specific operation of the first item is to perform the image expansion operation, and then the erosion operation The dilate operation expands the highlighted area of the image, and the erosion operation makes the highlighted area smaller, as shown in Figure 5. This operation further enhanced the vessel texture properties, making the subsequent binary operations more accurate. Finally, we need the binary image. First, set the threshold, and then set the pixel values outside the threshold interval in the image to 0, and then cycle the clustering from top to bottom as shown in the formula on the right. And finally, get the binary image we need. To save time, the formula are not described in detail. The above is a processor content, and the next is a classifier. As shown in the figure, it is mainly composed of two subnets, which process different input sources respectively, and combine the outputs at the fully connected layer. Next, I will introduce the relevant tricks of this neural network. We updated the traditional batch norm to layer norm, which realizes the characteristics of normalized dimension by calculating the mean and the variance of each batch of data, so it doesn't depend on the batch size and overcomes the shortcomings of the former. Then, the activation function is updated to GLU. It can be found from the figure that in a certain neighborhood of zero value, GLU has a large gradient, which means that the probability weight value of returning to zero is higher. That is, the network weight is more biased towards vascular distributing characteristics. Then, the optimization algorithm is updated to layer scale, which is a standardized method to maintain the consistency value of the layer and the magnitude of the gradient. Then, we also update the pruning algorithm to drop paths, which can automatically search for dropout patterns by adding unknowable hyperparameters named survival rate. That's all for our method. Next, I will present the experiments and results. We conducted comparative experiments in single source and multi-source respectively. The experimental results of the single source are shown in the table. For different data sources, ResNet and ConvNeXt perform the best. Therefore, ConvNeXt is used as subnet L, and ResNet is used as subnet ACE. Then, based on the results, for the multi-source experiments, the specific results are shown in the table. Among them, the final results of subnet L fitting the original image and subnet ACE fitting the binary image are the best performance. At the end of the experiment, we also visualized the interpretability analysis of the neural network. As shown in the table, here are three sets of examples. It can be found that subnet L focuses more on the local overall area of the image, while subnets pays more attention to the local detail area around the vascular. Finally, it's our conclusion. In the application of myopia classification of children's fundus images, we propose a new homogeneous multimodal method which allows the model to learn the information of the original image and the information of vascular features simultaneously to distinguish non-high myopia and high myopia. The results of different experiments show that our method achieved the best performance. Since there is no homogeneous multimodal scheme of fundus image combined with vascular features, our method is of great significance. This good result provides a good prospect for the clinical automatic detection of myopia in children. Thanks for listening.